Hello and welcome back to another video in our Thermodynamics 2 series. Today's video is really a continuation of one that we've just done, a brief one that we've just done on the properties of mixtures of ideal gases. And what we're going to do here today is we're going to introduce a model for how we can account for the individual contribution of the pressure of each individual constituents in a mixture of ideal gases. Previous video on properties of mixtures of ideal gases, we recapped on what the ideal gas model was. We talked about how it's a convenient model that's used for many important engineering applications, such as gas power cycles and refrigeration cycles that uses gas, among many other things. We've established how we're going to calculate the specific gas constant for an individual ideal gas and a single component ideal gas, and how that extended to a mixture of ideal gases. We've looked at the molar mass of the mixture of ideal gases, and we ended up with an example where we calculated all that, both the average molecular mass of the mixture of ideal gases as well as a specific gas constant for the specific case of atmospheric air, and found out that the molecular mass of atmospheric air is roughly 29 kilograms per k-mole, and its specific gas constant is about 287 joules per kgk. So numbers that become very handy in a lot of engineering calculations using air in real life. Now, looking at this example with air, I have three different ideal gases making up atmospheric air. A valid question would be, well, what is the relative contribution of each of these gases to the overall pressure that the mixture of ideal gases has on a container, let's say, that it's stored into? Now, we know that the pressure due to a gas is a function of the collisions between the molecules of that individual gas and the confinements of the container in which it stands, for example. And so it's a valid question to wonder, well, how do we segregate each of these individual gases when they are all mixed together within a single container? And one model, the model that we're going to deal with today, Dalton's model, tackles that question by stipulating that each of those gases in the mixture of ideal gases, each of the individual constituent ideal gas behaves within the container as if it alone was in the container. In other words, there's really no contribution to the total pressure due to individual molecules hitting one another of the different gas species. Only the individual species acts as if it were in that container all by itself. So therefore, if we know the individual partial pressure of each of those individual gas components, simply by adding them all up, we're going to get the total pressure inside the container. And you might think, well, that's an interesting stipulation, but how good is it in real life? And because the relative space of each of these individual molecules is so small within the mixture, it turns out that there are very few interspecies collisions taking place within a container that would add to the overall pressure. And as a result of that, the total pressure predicted by Dalton's Law model for mixtures of ideal gases is incredibly accurate. So it's a very good model for dealing with mixtures of ideal gas. So let's sum this up right here. Dalton's Law. For mixtures of ideal gases. So to summarize what I've just said, for a mixture of ideal gases, for a mixture of ideal gases. Each species, so each individual component in the mixture, behaves as if it was alone in the mixture, at the same volume and temperature as the mixture. Same volume and temperature establishes the confines of the container in which it's at. This is what we call Dalton's Law. That's a statement of Dalton's Law. Okay, let's box that up. So in the case of air, for example, we would be looking at nitrogen, argon, and oxygen separately within the container, and looking at each of these pressures independently. So each species exerts a fraction of the full pressure on, I'm going to call it the container, whatever the surroundings are. Brackets here to really illustrate that we're talking about the surroundings in general. And that pressure due to each individual subcomponent of the mixture, the individual species ideal gas within the mixture, is what we call the partial pressure of that gas. So as before, we're going to denote a piece of I to denote the partial pressure of component I within the mixture. That's going to be equal to, since gas I is itself an ideal gas, is going to obey the ideal gas law. So I can cast it in the form of the ideal gas law that's based on number of moles, which is PV is equal to nRT with the universal gas constant this time. And since my temperature and my volume is the same as the overall container volume and temperature, then these terms are not changed, right? And for the whole mixture, similarly, as we've established that is itself is an ideal gas, then this must also be true that the total pressure that we would measure if we were to sense what the total pressure of the combination of all these ideal gases within the container is, must be equal to the total number of moles within that container times the ideal gas constant times the temperature of the container divided by the volume of the container. Right, so if it's true for each individual ideal gas and the mixture is itself an ideal gas, then this must also be true, right? So if we divide those two expressions together and bear in mind that the pressures again are in absolute units, as is the temperature, then what we're going to find is that the ratio of partial pressure to the total pressure must be equal to that top equation divided by the second one. And let's take it step by step here. Let's not skip a step. Divided by total number of moles times universal gas constant times temperature divided by volume. And of course, we've got that the universal gas constant and the numerator and denominator cancel, as do the temperature, since that is unchanged, as do the volume since this is unchanged. So all we're left with is that the ratio of pressure of that individual ideal gas divided by the total pressure in the container must be equal to the number of mole of that constituent divided by the total number of mole of gas within the container as a whole, which we've already defined as the mole fraction Y sub I. So the fundamental result of Dalton's law is that the individual partial pressure of a gas in a mixture of ideal gas is simply equal to its mole fraction in the mixture times the total pressure that would be measured for that gas. That is key statement of Dalton's law right there. So it's a rather simple yet concise law for ideal gas, but a very powerful one. And again, by definition of partial pressures, P, the total pressure, is simply going to be the sum of all the partial pressures of all the constituents that we have, right? So all of these partial pressures add up to the total pressure that we have, and voila, that's it. So we could repeat the analysis that we did before with respect to the air, and we can do it right now. It's quite straightforward, clearly to apply. For example, for atmospheric air, say in a container, stored in a container at 100 kilopascal, 25 degrees Celsius, and 1 meter cube. What we are saying is that if the makeup of that atmospheric air is 78% N2 as before, 21% O2, and 1% argon, then what that means is that the partial pressure of nitrogen in that mixture is going to be equal to the mole fraction of nitrogen times total pressure that we have in the container. So that's going to be 0.78, because the mole fraction is the same as the volume fraction, times 100 kPa, because that's the total pressure given to us, or that the partial pressure of nitrogen is going to be 78 kilopascal for that container. Similarly, for O2, I think it's quite clear that you can expect its contribution to the total pressure to be 21 kilopascal, whereas for argon, its contribution is going to be 1 kilopascal within the container. So that's how we would use Dalton's law to figure out the individual pressures for a mixture of ideal gas. Okay, moving on to other properties, extensive properties in a mixture of ideal gas. For example, the thermal energy, enthalpy, the entropy, and the specific heats at constant pressure and constant volume specifically. How can we figure this out for the mixture of ideal gases if we know what these are for each of the individual constituents? Obviously, the contribution of each constituent, the total thermal energy of argon, for example, in the air mixture, and the internal energy of oxygen and nitrogen, should add up to the total internal energy of air within the container, if that's the mixture that we have, because all these individual properties are extensive, which means that they are additive, regardless of how the container is subdivided. That's the whole meaning, the whole point of an extensive property is that it's additive over its subsystems. So that should fall over naturally. So that suggests or explains that the total internal energy or thermal energy of the system is going to be simply the sum of the extensive thermal energy of each of the constituents. And similarly for the enthalpy, right? Also on a molar basis, I'm going to have that the total intensive internal energy per mole is going to be the total extensive internal energy of the total mixture divided by the total number of moles in the mixture. Similarly, for the enthalpy, it's going to be the total extensive enthalpy divided by total number of moles in the mixture. So this means that if I take the total number of moles that I have in that mixture and I multiply it by this molar internal energy for the entire mixture, that's got to be equal to capital U, which is itself going to be equal to the sum over each constituent of each constituent's internal energy, molar internal energy, and same with the enthalpy, which means that, like we did in the previous video, that the molar internal energy is going to scale like the mole fraction by bar. If I know the individual molar internal energy of a gas mixture, then to find the total molar energy of the entire mixture, it's simply going to be the sum of all these individual molar internal energy times their mole fraction of the mixture. And without going through every step, you can see that the same thing applies for enthalpy. Similarly, on a mass basis, this one here was on a molar basis. Let's repeat the whole thing on a mass basis. On a mass basis, now the internal energy is simply equal to the very same extensive energy that we found before, divided by the molar mass of the mixture itself, and with enthalpy. And this is maybe the property that we use more as opposed to the molar one. So that's going to be equal to the sum of the molar masses of each individual component times their own internal energy divided by the mass of the mixture again. That's going to be equal to the mass fraction, the sum of the mass fraction, which we talked about in the previous video, times the individual internal energy. That's it for that. And similarly for the specific enthalpy of the entire mixture, that's going to be equal to the mass fraction of each individual component times the individual component's specific enthalpy. So this is through because, again, important results that we're going to use many times. Finally, dealing with the specific heats, recall the definition of specific heat at constant volume. It's the derivative of internal energy with respect to temperature, keeping the volume constant. And since we've just defined what that internal energy is, say on a mass basis and on a molar basis, let's start with the molar basis. We did this first. We're going to have a specific heat on which is going to be joules per k-mole Kelvin, is going to be equal to the rate of change of internal energy, molar internal energy, for the entire mixture with respect to temperature at constant volume, which is going to be equal, as we saw above in that box equation above, the sum over all mole fractions of each of the constituents times their respective molar internal energy, keeping volume constant, which is the same as saying d dt of u bar at constant volume. Okay? And so, of course, each individual mole fraction is not a function of temperature, whether it's at constant volume or not. So we can take the derivative on the inside of the summation here on a per component basis and pull that y out of the derivative, so that we're going to get that this is equal to the sum of individual mole fractions times ddt of the individual molar internal energies of each of the constituents. But each of these guys, of course, is simply the molar specific heats at constant volume for that particular component. So what we're left with is a nice expression here for the specific heats in terms of the specific heats of each of the components. A little break here. All right, and because the mole fraction of each of the constituents is not a function of temperature, we can take the derivative inside that summation here, which gives us the summation of over each of the constituents of y sub I times ddt of the molar internal energy at constant volume. And of course, we recognize here that that guy right there is itself the specific heat at constant volume of constituent I, which simplifies the result a little bit more to the molar sum, the sum over each molar fraction of the specific heat at constant volume for each of the components. Quite a nice result. So really, for mixture of ideal gas, everything simplifies quite nicely. And similarly, without going through the same derivation, you can readily see that the specific heat on a molar basis for the mixture of ideal gases is simply going to be the summation of each of the individual ideal gas component times their mole fraction within the mixture times the molar specific heat at constant pressure for each of the individual constituents. And on a mass basis, the specific heat at constant volume is going to be equal to the sum of the mass fraction, not the mole fractions, for each of the individual components, times their own specific heat at constant volume. Voila, and same with the specific heat at constant pressure. Again, on a mass basis, the properties that we tend to use more often in our applied engineering applications rather than on a molar basis from before, but I think it's good to have perspective where we're looking at both of them individually as well. So we're going to highlight all of them equally as we've just done here. And finally, the entropy is, because it's an extensive property, is also going to scale like the sum of each individual entropies over the entire mixture. So this guy here is the specific entropy on a mole basis of constituent I per mole of I. And we could have done the same thing on a mass basis, right? So S for the mixture is going to be equal to the mass fraction of I times the mass, let's put a bar right there, on a per mass basis right there. Specific entropy per mass of I per kg of I. Voila! That's our mixtures of ideal gases. Enjoy and talk to you soon.